Hey guys, Miss Gill here. Today we are going to start a new topic, still dealing with exponents, but it's a new topic. Understand scientific notation. So this is a new lesson. It's module 12, lesson 2, and it is an apply and practice lesson. So there's no build understanding for this lesson, but the step it out to me is kind of like the build understanding part. So we're going to work out some things, learn about writing in scientific notation, learn about writing it from scientific notation to standard form, and a few different things. So as we go through, if there's a part where you start feeling like you're understanding it, pause the video, try some of it out, and then you can always check the video out and fast forward through the parts that you have determined you're good at and that you don't need. Alright, so let's get started with the I can statement. I can use scientific notation to describe very large or very small quantities and to compare quantities. So that's the main idea of scientific notation. It's writing a number that is really big or a number that is really small. A lot of those really small numbers y'all still like to call big, even though it's technically just a long number, and we'll look at the difference between a large and a small number. All right, so step it out part 1 says, what does $1 trillion look like? If you could stack 1 trillion $1 bills, the stack would be about 68,000 miles tall. Wow. This is more than 1/4 of the distance to the moon. The standard or decimal form of a number is one way to write numbers. It uses the base 10 system to show all of a number's digits. For example, the way to write 1 trillion in standard form is 1 followed by all of those zeros. There is a shorthand way called scientific notation to write large numbers without so many zeros. So the number 1 trillion in scientific notation is 1 times 10 to the 12th power. And so in the previous lesson, we talked about some powers of 10, and we talked about how this exponent 12 would be the number of zeros in your standard form. Your problem of the day from yesterday or Tuesday also had you work on something like this, and this is why it was chosen as the problem of the day. So to write 68,000 miles in scientific notation, you first move the decimal point to the left to get a number that is greater than or equal to 1, but less than 10. So basically what that is saying is move the decimal to the left until there's only one digit in front of the decimal that's not a zero in this situation. So if we look at it, they started here and they moved it until it was behind the 6. So that would be the first non-zero digit. It is also the number that is greater than or equal to 1, but it's less than 10. So there's only one digit in front of the decimal when you're dealing with scientific notation. So the decimal point moves 4 places to the left. And now it says remove the extra zeros to get the first factor for this scientific notation. So if we take out these zeros, we would now have 6.8. It says use this factor and a power of 10 to write the number in scientific notation. So we would start off with the 6.8, and then our exponent is just going to be the number of times we moved our decimal. So you may want to make a note of that for your notes. If you don't have these papers, that's fine. You can jot down some stuff on a scratch paper, or you could take a picture, like screenshot it, so you have it for reference. So this exponent here is the number of times that you moved the decimal. And I also will have these notes up on Focus and on the Files tab if you would like to be able to reference these at any time as well. So that is the number of times you moved the decimal, which we got right here. We moved it 4 times. And so we kind of already talked through the scientific notation vocabulary. You can read it again if you like. But we're going to move on to part C. So now it says, write 1 billion in scientific notation. So we need to know what exponent goes here. If we move our decimal, we would move it 3 for those zeros, 3 more, and 3 more. So we would have a total of 9 times that we moved our decimal. So that is your exponent. And we moved it to where there's only one number that is greater than or equal to 1 but less than 10 in front of the decimal. And so this would be written as 1 times 10 to the 9th power. So I've been skipping over some of these turn and talks, but I really like this turn and talk, so we're going to do it. Is the number 16 times 10 to the 7th power written in scientific notation? Why or why not? I want you to think about that for a second. What would you say if you're in the classroom right now and not watching this on a video? So remember, the definition of scientific notation said that we move the decimal to where there's one digit in front of the decimal that is greater than or equal to 1 but less than 10. So 16 is not less than 10, so therefore this would not be written in scientific notation. And what we would need to do is move the decimal one more time, and then that would be 10 to the 8th power. So I'll go ahead and answer this in words. So no, 16 is not greater than or equal to 1 but less than 10. So this written in scientific notation would actually be 1.6 times 10 to the 8th power. So that's how that number should be written in scientific notation. All right, we're moving on. All right, so you can also use scientific notation for very small numbers. So remember I told you, you still think of these, or most of you over my years of experience still think of these numbers as big numbers because there's a lot of digits. But technically this is a very small number because it is a number less than 1. Excuse me. So they get kind of long, and so because there's so many numbers, you're like, oh, that's a really big number. But in reality, it's actually a really small number. So we're going to write this quantity 0.0043 inches in scientific notation. So in the last one, we moved the decimal to the left to only have 1 digit in front. Now we're going to move the decimal to the right to where we only have 1 digit in front. So we would have to move it 3 times. And I might have just said that backwards, and if I did, I apologize. For the numbers greater than 1, we move our decimal to the left. For numbers less than 1, we move our decimal to the right. So I apologize if I misspoke earlier. All right, remove the extra zeros to get to the first factor. So we're going to take out, we don't need those zeros anymore now that we moved the decimal, and we would have 4.3. So, just like before, the number of times you move it becomes your decimal. The only difference is, since this is a number less than 1, your power of 10, the exponent, will be negative. So instead of being a positive 3 this time, it's a negative 3. So it would equal 4.3 times 10 to the negative 3. All right, let's move along. So now we've looked at an example of a number larger than 1 and a number smaller than 1 to write in scientific notation. So now we're going to practice them. Then we're going to work on comparing them. All right, and it's not as bad as it sounds. So in 2016, the United States Mint produced about 9.1 times 10 to the 9th power pennies. Write this quantity in standard form. So standard form means a number without decimals. That's all it means. Use the power of 10 to determine how many places you will need to move the decimal point. So remember, the exponent tells you how many times to move your decimal. All right, exponent tells you how many times. So move the decimal point. What's our exponent? 9. So we're going to move it 9 places. Write the number with the placeholder zeros, then move the decimal point to the right by the appropriate number of places. So they went ahead and put some zeros in there for us. If you didn't have this already written out, what I would do is I just put 9.1, I write it down, and then I go ahead and move my decimal, and then I add in the zeros. And I'll show you an example. We'll get to one later where I do that. So we have to move it 9 times, so it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So our decimal is going to be behind there. So to write this out, they conveniently already put all the zeros there, so we're going to write it out like that. So that was 1, 2, 3, 4, 5, 6, 7, 8 zeros. So 1, 2, 3, 4, 5, 6, 7, 8 zeros. And if you want to be, I don't want to say grammatically correct because this is math, but normally every 3 numbers we put a comma, so that would make it, I don't really know what the word, it would just make it look more professional, more appropriate. All right, would you get marked wrong if you don't put the commas? No, I doubt it. All right, so let's see. Scientific notation makes it easy to compare. So now we've done 3 different types of examples. The first question we did is we took a scientific notation number that was greater than 1 and made it a larger number using scientific notation. The next example, we did a number less than 1 and wrote it in scientific notation. In this number 3, this third example, we took a number in scientific notation and wrote it in standard form. All right, now we're going to compare them. So we're going to need to use both methods to compare them. So what I mean by that is using the scientific notation and writing in standard form. So as the scientific notation makes it easy to compare quantities. The table shows the number of half-dollar coins produced in 2016. Use a ratio to compare these quantities. So remember, ratio, think fractions, think division. It isn't that bad because we have calculators, so don't be like, oh, Ms. Gill, why do we got to do fractions? I told you by the end of the year that would become your new favorite F word because fractions aren't that bad. All right, so let me move my paper up some. All right, the table shows we've looked at this, so we're going to use a ratio to compare these 2 quantities here. So really what you're doing is you're breaking up this first part and you're actually going to divide that. But since we have to use calculators, we're going to divide it in a calculator. Now that you've learned the exponent rule from last lesson, you know when you divide exponent or powers that have the same base, you subtract their exponents. So and that's what they did here. The powers of 10 are the same, 10 to the 6th over 10 to the 6th, which equals 10 to the 0 or 1. And another way you could think about it is any number divided by itself equals 1. That's why this rule works the way that it does. All right, so now it says compare the first factors. So we're going to do 4.2 because you're going to take the larger number and divide it by the smaller number every time to do these ratios. All right, so it says compare the first factors. So really what that means is divide them. All right, so we're going to bring out that handy dandy calculator. We're going to put 4.2 divided by, because remember fraction means division, 2.1, and it equals 2. So that equaled 2. So the total number of half-dollar coins minted is about 2 times 1. So we're taking this number here, multiplying it to this number here. Okay, so 2 times 1 equals 2. 2 times the number of half-dollar coins minted in Denver. So this gives you a step-by-step way of comparing them. You can also take it just like this and say 4.2 divided by 2.1. Put it in your calculator. We got 2 times 10, and then we know we subtract our exponents whenever they're being divided. So 6 minus 6 gives us 0. So 2 times 10 to the 0 power, which equals 2 times 1, which equals 2. So same idea as here. Just not written out in the same kind of format. So if you're I don't really like going through this. This seems like it's taking a really long time. This is another way that you can work it out. All right, turn and talk. I like this one again. Why is scientific notation a good way to express very large or very small numbers that you are estimating? So why is it a good way? If you've noticed, some of these numbers are really large. Some of them are going to be really small but really long. And so our fingers have to work with our brain and actually put all those numbers into a calculator, which guess what? We make mistakes all the time. That's why in class I always tell you to check your answer twice just in case. So by using scientific notation, it reduces our errors in calculating it, because now we don't have to type in, oh, did I type in 5 zeros or did I type in 6 zeros? I don't recall. Let me start over. So then that way it just makes things a little easier to calculate. So that would be a reason why using scientific notation could be helpful. Plus you have to know it for science, so it helps out with that too. All right, let's move on. All right, we're on the last page. So it says use the ratio 3.45 times 10 to the negative 8 over 3.45 times 10 to the negative 11 to compare 3.45 times 10 to the negative 8 and 3.45 times 10 to the negative 11. First, compare the powers of 10. Compare the greater power to the lesser power. So remember, the higher the exponent, the greater the number. All right, so in this case, negative 8 and negative 11. Negative 8 is closer to 0 than negative 11 is, so negative 8 is greater. All right, we will look at some more of this, but just remember, the greater the exponent, the bigger the number. So that means that we're going to put the 10 to the negative 8 on the top. And so I'm going to work this out to the side and then put my answers in here, because many of us tend to forget a negative. So remember, we have to subtract our exponents when they're being divided. So we're subtracting them. But our exponent isn't positive, it's negative 11. So many of you recall from your integer rules last year that when you have two negatives together, they become a positive. Just like a negative times a negative is a positive. So now you have to treat this as 10 to the negative 8 plus 11. And so if we add integers with different signs, we subtract their absolute value, take the sign of the bigger number. Right, so 11 minus 8 is 3, and the bigger number in this case is positive, so this would be 10 to the third power. All right, and now we need to write it in standard form. Remember, I told you the trick. The exponent tells you how many zeros you should have in your answer. Next part says compare the factors. So we're looking at the first two parts. So we just did this part here. Now we're going to compare this part here. So we have 3.45 divided by 3.45. Well, any number divided by itself equals 1. So 3.45 times 10 to the negative 8 is 1 times 1,000. So we're multiplying these numbers that we got. So your power of 10 times your factor. So 1 times 1,000, any number times 1 is itself. So it is 1,000 times greater. So 3.45 times 10 to the negative 8 power is 1,000 times greater than 3.45 times 10 to the negative 11. And like I said, guys, if you're starting to get this and you feel good about this, you're welcome to pause the video right now, try C, and then see if you got your answer right. Okay, if not, then find out what you did wrong. All right, use a ratio to compare 4.8 times 10 to the 9th power and 12 million. So first, before we can do this, we can't compare them in two different types of notation. So we're going to turn the standard form into scientific notation form. So we need to move the decimal. Remember, your decimal starts behind. So here would be 3. This would be 3 more. And then we need just one digit in front of the decimal. So that would be a total of 6 plus 6. 6 plus 6, really? Sorry, guys. 1 plus 3 plus 3 is 7. I get ahead of myself sometimes. Sorry. All right, so that, remember, is our exponent. So we have 1.2, because you can't forget the non-zero numbers. They all have to be there. Even if there was a 0 and then a number, you still got to have that number, or you're going to end up with a different answer if you tried to convert it back. So all non-zero digits must be in there. All right, so 1.2 times 10 to the 7th power. So now, because this exponent is 7, this one is 9, that means this one's the bigger number. So that one's going to go as your numerator. This one will be your denominator. So we start off with the powers of 10. So we have 10 to the 9th over 10 to the 7th. Remember, the rule says you subtract your exponent, so 9 minus 7 is 2. And then if we write that out, 10 squared is 100. Our exponent 2 tells us there's 2 zeros. Now this only works for numbers greater than 1. So when it's negative, it doesn't work like that. Only when it's positive. All right, so compare the first factors. So we had 4.8, and then in this one we got 1.2. And when it says compare, it really means divide, but it knows that you guys cringe at that word. So we take out our calculator, put in 4.8 divided by 1.2, and we get 4. So 4.8 divided by 1.2 is 4. So now what we say is we put a 4 here and times our power. So 100, 4 times 100 is 400. So 4.8 times 10 to the 9th is 400 times greater than 12 million. So that means if you took 1200, multiplied it by 400, you would get this number. All right, last one before check understanding. And the check understanding is actually quite easy in this one. Use a ratio to compare 0.00222 and 66,600. Why they do these numbers like this is beyond me. I think they do it to torture those who that number makes them cringe, but whatever. So it says in scientific notation, so we got to rewrite this one in scientific notation. So remember, we want one digit in front of the decimal. You will be tempted to bring it all the way to here, but don't do that because that would be more than one digit. So when you're going this way, we want it to stop right here behind the first 2. So we would move the decimal 1, 2, 3 times. All right, move it 3 times. So that would give us 2.22 times 10 to the 3rd. If you move it 4 times, that would technically be 22.2 times 10 to the 4th. So that would not be correct scientific notation. All right, this one says to write this one in scientific notation. So we start back here. We have to go up 1, 2, 3, 4 times. So this would be 4 times we would have to move the decimal. So we get 6.66 times 10 to the 4th. And yes, that does hurt saying that. All right, so because this exponent is greater than this one, that one means this is the larger number, which we can tell that this number is larger because it's greater than 1, where that one is small, less than 1. Oh, did y'all just see my boo-boo? Because I'm glad I just talked about it, because I just saw my boo-boo, and yes, I said boo-boo. This should not be positive, Miss Gill. That should be negative. Glad y'all caught that. Hopefully some of y'all were fussing at me at the video. All right, so this should actually be -3 because it is a number less than 1. All right, so now we need to know how many times greater is 66,000 than 0.00222. How do we do that? So remember, we have to set up the ratio. So I'm going to set it up over here. we have 6.66, because remember this one's greater, over 2.22 times 10 to the 4th, because we're going with the greater number first, and then 10 to the negative 3. Because if not, you would get a decimal. And so say your decimal is 0.0056. So that number is 0.0056 times greater. And you're like, what kind of times is that? So anyway, that's why it's best to put the largest number first. All right. Enough with me rambling. So if you put this in a calculator and divided it, you would get 3. So that number goes into that number 3 times. Just trust me on this one. Then we have 4 minus negative 3. So remember, when we subtract a negative, it's like adding. So instead of 4 minus negative 3, it's going to be 4 plus 3, which would be 10 to the 7th power. All right, I'm going to show it actually written out just for those of you that are like, what? How did you get that? All right, so 10 to the 4 minus negative 3 is the same as 10 to the 4 plus 3, which is 7. All right, so we get 3 times 10 to the 7th, which would be 3. And remember, we add 7 zeros. 1, 2, 3, 4, 5, 6, 7. And I'm going to put my commas in, so that would be 30 million times greater, which is to be expected because that's a really small number. All right, so hopefully so far this has helped. If not, there's always the help session that you can join live, or you can reach out to me and say, Ms. Gill, I watched the video, still struggling a little bit. Can you help me? And we can set up a time to meet. So let's check our understanding right now. Sorry, my phone's ringing. Okay, sorry about that. So check understanding. I'm going to put it up here, and then I want you to pause the video. Usually during the live lesson, I give about 5 minutes to do this one, but this one to me doesn't take 5 minutes. So pause the video, work out the questions, then unpause it and see if you got the answers right. But please pause the video and actually try it. If you get stuck, I understand, but actually give it a good effort. Okay, so hopefully you paused the video and you gave this a try. And it says, which number is greater? 8.9 times 10 to the 5th or 2.1 times 10 to the 7th? How can you tell without writing the numbers in standard notation? So I said this earlier in the video. We look at the exponents. All right, the greater the exponent, the larger the number. So 2.1 times 10 to the 7th power is the largest number. It has a greater power of 10 would be an explanation. It has a greater power of 10. So it says write this one in scientific notation. So we need to move our decimal. Remember, only one place in front. It's very easy to try to go all the way to leave one, but in this case it's different. So 1, 2, 3, 4, stop behind the 5. So this would be 5.01. Yes, you write that 0 because it's in between two non-zero numbers. All right, times 10 to the, how many times did we move our decimal? We moved it 4 times, but because it's a number smaller than 1, it's negative. All right, and remember how I told you if they don't write the zeros out for you, you can add them in. So I'm going to show you what I meant by that in this one. So our exponent is 3. That means we need to move our decimal 3 times. So 1, 2, 3. So there should be a 0 there. So if you went on more, you would just add zeros in all of those little loops. So this would be 5,310. So great lesson today. I hope you're able to take this information and help you with the Into Math. But if not, join me for the help sessions, ask questions. Also reach out to me on Teams or through text and I can help as well. If it's just that I keep getting the wrong answer, take a picture of your work, text it to me, and look at it from there. All right, have a great day.